Hi everyone, my name is Da Hong Zhang, and I'm currently pursuing my master's degree in Cornell University, and I'm also previously the undergrad student from University of Toronto. So it's happy to be here. And at the beginning of the meeting, Arthur and Professor Gruninger has mentioned the female ontology, and it's actually the capstone project I did in the last year of my U of T journey. So in my presentation today, I would zoom into the female ontology with more details of the implementation. So just a quick overview of what we are going to talk about today. So first, I will do a quick introduction to the problems we are trying to solve in our research and what is our objective. And then I will do a quick introduction to the state-of-the-art ontologies in the market, and also how we're going to integrate all of these ontologies, the existing ontologies. And then we will also extract the information from the knowledge graph to see how they can answer some questions. And at the end of the meeting, I will also discuss some future application of our research and wrap up the meeting. So based on our research and the interview with the farmers, we found that one of the biggest challenge for the farmers is actually the unpredictable climate change. The climate change can actually lead to some challenge for planning the irrigation, and it can directly impact the production yield of the farm. So the farmer said this is like one of the biggest challenge. And the other challenge that we identify is that sometimes when farmers are discussing with their stakeholders, like the buyers and the suppliers, since the stakeholders don't have like perfect knowledge of like agriculture and the farms, so sometimes there could be some miscommunication and inefficient negotiation between the farmers and the stakeholders. So this is another challenge we identified. And in order to overcome these challenges, our objective is to develop a systematic approach to represent the relationship between the farm, the agriculture, and the climate. And also, in order to apply this in real world, we also want to store the data within this relationship. So one of the solution we came up with is the knowledge graph. And knowledge graph is actually the integration of the data and the ontology. By definition, the ontology is the term that could be used to represent the shared knowledge and shared understanding of a specific domain. And it can perfectly resolve the first part of our objective, which is to represent the semantic relationship between the farm, agriculture, and climate. So the data set we would use in our project is the Canadian government climate data, and it's actually the time series data of the weather in Canada, and it involves the rainfall level, soil moisture content, and different other data. And then we also have the farm data, which is the geographical coordinates of the farm and field. And for both farm and field, they are gonna spatially divide it by the polygons, and the database is gonna restore the coordinates of the vertex of the polygons. And in terms of the ontology, since we do not want the ontology to answer like every single questions of the world, we need to define some competency questions to restrict and narrow down the scope. So based on our research, we think one of the questions that the farmers really want to be asked, we really want to be answered, is the when will the next rainfall first become available to my farm? And the second question would be, what is the precipitation level that may impact my field and my farm? And the last question is, what is the optimal irrigation schedule for my crops? For the first two questions, they are kind of like a descriptive questions that can easily be retrieved and queried from our graph. And for the third question, it will involve some analytics tool based on the information we extract from the graph. So in terms of how we can integrate ontologies and develop it, there are actually two ways we can do that. First of all, we can do it like starting from scratch, but this is time consuming and inefficient because nowadays there are a lot of research related to ontologies, and there are a lot of concepts and relationships that we can reuse. So a more efficient way to develop ontologies by integrating them. So there are many state-of-the-art ontologies that are related to the topics we are discussing. So first is the suite ontology that is mentioned earlier in today's meeting. So suite ontology is developed in 2005, developed by NASA, and it involves the classification of the concepts in Earth system science, which includes the representation of the space and time, the process of different physical and chemical objects, and also the human activity. And later on, after the development of the suite ontology, there's also a famous ontology called soil, because in our scope, we're trying to resolve the problems for the farm. And so soil is really important concepts that we need to reuse. And the soil ontology developed in 2006. It reuses some high-level classes from the suite ontology, but further extending them to provide more details about how the soil properties and process are interacting with each other. And in addition to these two ontologies, the time ontology and geosparkle ontology are also important, because time ontology is used to justify whether the specific event is like before or after a time point. And for sparkle, a geosparkle ontology, it's used for spatial reasoning. So for example, it can be used to justify whether two areas and regions are actually overlapping or containing each other. So by integrating all of these four ontologies, we have developed an initial prototype of the female ontologies. And then I would discuss how we implement the integration in details. So for the first step of the integration, we use a technique called modularization. And the reason why we're doing this is because suite ontology is like a huge ontology with over 10,000 concepts and 300 properties. If we integrate such a huge ontology entirely, it will lead to memory overloading. And because the soil ontology also reduces some suite ontology, so we don't want any redundancy happening in our ontology. So the key idea of the modularization techniques is to find an upper level class of the concepts that we have. And by climbing up the hierarchy, we want to see if there is any branches connected to the hierarchy. And if there is, we need to incorporate this this hierarchy as well. And the ending point of this modularization is when we find the highest level class. So it may be a little bit confused when I explain this, but I will walk through a quick demo on how we extract the concepts we need. So on the right of the graph is the female ontology, which is the concepts that we need, which is the farm, field, and crop. And on the left-hand side is actually the structure that we extract from the suite ontology. So in the red box is the farm concept. and we define it as a subclass of the form. It may be a little bit confused why we're doing this. This is because the form in blue and the form in white is actually in different namespace. And the form in Sweet Ontology may have more general definition of the form. It can be like the form in everywhere of the world. But the form in our concept is basically just for the form in the data set we have. So we believe it's like a narrower definition. So we define it as a subclass relationship. And by climbing up the Sweet Ontology, we can find that farm is a subclass of a agricultural production facility. And it's also a subclass of a facilities. And by doing this repeatedly, we find that the substance is actually the highest level class of the Sweet subset. So then our modularization process can stop. And also in this case, we didn't find any classes that are connected to the agriculture production facilities. But if there are some axioms or any relationships that are also connected to this hierarchy, we need to extract all of this in order to avoid any conflicts in terms of the logics. So this is how we implement the modularization. And the next step is to incorporate our Sweet subset with the other ontologies. So since we have the soil ontology and also the female ontology concepts that we created ourselves, and this is the overall structure of how we combine them. The red box here is the Sweet ontology, and now we move to the soil ontology, which contains the contains two important concepts, which is the precipitation and the soil moisture content. They are particularly important for our project because our data set are mainly describe the soil, the relationship of the soil and the precipitation, and our data we're going to be stored into these two concepts. And precipitation has a subclass called rainfall, and we will store our historical rainfall data into the historical rainfall concept or class. And the next step is how we, since the structure of our ontology has been developed, now the next step in order to integrate with the data, we need to transform the relational database into the RDF triples. Since all of the data we have nowadays is the relational database, which is like a CSV file and a table, we need to transform each rows into different RDF triples by the following ways. So for example, suppose I have a special rainfall event in on May 1st, 2015, and its amount is 800. The soil moisture content is 21%. We would need to first initialize an instance of a rainfall event and make it as an instance of the historical rainfall. And then for this rainfall event, we will connect this instance with the data with a relationship called has amount. And similar for date, we will need to connect this event with the date with a relationship that we borrow from the time ontology, which is in XSD date. And similarly for soil moisture content, we can do the same thing. And then this is how we're going to transform the relational database to the RDF triples. So after developing such knowledge graph, we need to evaluate effectiveness of this knowledge graph and see how we can answer the questions to our competency questions. So to query the knowledge graph, we will use a special language called Sparkle, and it's pretty similar to SQL, the SQL, but Sparkle is only tailored for the graph database retrieval. So I will run through two examples in order to see how our graph is going to answer the competency questions. So for the first competency questions, it's like, when will the next rainfall first become available to the farm? In these questions, what we need is the date of the rainfall level that is greater than 0. So in order to write this query, we need to first select the date, and then we will go to this row. And this basically what this is mean is that what instance actually has the relationship of has amount, and we will retrieve all of this relationship. And the next slide is similar. We will retrieve what kind of instance, or what pair of the instance we have are connected with the relationship of in XSD date. And the bottom table is actually the results. We can retrieve the date and the time that has the rainfall level greater than 0, which is what we need. And on the right-hand side is the second competency questions, which is what is the precipitation amount that will impact my field? The query here is actually more complicated, but it's actually following the same idea as the left-hand side. So this is how we're gonna retrieve information from the knowledge graph. And there's always a debate related to why we don't use relational database, is that why we're using the knowledge graph. And this is because in this scenario, we believe the knowledge graph will have more strengths over the relational database. So the first, one of the biggest strengths that we think is the semantic explainability. So no matter for the query or the relationship we see in this graph, all of the relationship, the subject, object, and predicates are actually pretty similar to our daily natural language. So it's easier for the people who do not have like a specific domain knowledge to use this graph and use the query. And the second strength of the knowledge graph is the flexibility. So for example, if I would like to integrate with new concepts and new ontologies, we can just easily create a new relationship between these ontologies, and it can form a new ontology. But for relational database, if we want to combine two unrelated tables, we need to create some mapping keys in order to connect these two tables with like totally different information, and that would be a little bit inefficient. So that's the second strength. However, compared to relational database, there's also some disadvantage or weaknesses for knowledge graph. One of the biggest weaknesses for knowledge graph is the challenge of data partitioning. So data partitioning is the process of divide the graph into the subgraph. Although we have shown the techniques of the modularization, when the connection and the ontology and knowledge graph has a really complicated relationship and have a lot of like concepts, it's still challenging to divide the graph into different pieces, and it actually has a lower efficiency in terms of the data partitioning compared to the relational database. So but in our scenario, since we have successfully performed the modularization stage, we think this weakness is not a major concern of our research. So this is the reason why we use knowledge graph instead of the relational database. And Due to the success of our knowledge graph, we believe it can be integrated and applied to other areas of the world and also other industries. One of the biggest application that we believe it can be applied to is the financial industry. Since our current knowledge graph only contains the knowledge of farm, agriculture, and climate change, by integrating such financial ontology, it can helps particularly for the banks to evaluate maybe the credit risk of the farmers, and also help the banks to do a more efficient and appropriate investment to the agriculture and the climate change. And the second application is the digital twin. So by the time of this project, we actually have another team to develop a computational layer for this digital twin. And the computational layer is actually the tools to help the knowledge graph to be automated. So if the computational layer and the knowledge graph can be combined to form a digital twin, I believe it will have like a positive impact to the society. And the last but not least application is the large language modeling, which is also mentioned in earlier in today's meeting. So there's a lot of research have shown that large language modeling has a better interpretability on the knowledge graph instead of the pure text. So for example, if you want to ask the GPT to answer a specific question, if you just ask GPT with pure text, it may not have like a perfect knowledge of what you're asking. However, if you use the knowledge graph to feed into the large language modeling, it can explain and understand the knowledge better. So yeah, so to wrap up today's my speech, I would like to say that our ontology design successfully helped the farmers and the stakeholders to understand the knowledge of farm, agriculture, and the weather, and it can further support the process of irrigation. And also the techniques of the modularization leads to a more manageable and efficient structure of the ontology. And this, our competency questions can be actually queried by the Sparkle query, and it can demonstrate the semantic explainability and flexibility of our design. So all of these methodology presented in this research, we continue to apply to different industry, and we believe it will generate great impact to the society. And at the end of the meeting, I really want to say thank you to RBC, and also a big thanks to Professor Gruniger, Arthur, and Jeanette for supporting my paper, supporting throughout this project. And I'm open to any questions now. Thank you.
Very great job. Thank you so much, Dong. That was really well presented. It did give rise to conversation in the chat there, which I think we sort of resolved, but I'm not sure if you might have a perspective on it. And really, the original question was: is the work that you did, does that fit into a data science person, or does that fit somewhere else? And my suggestion was, no, it's something you could train a data scientist to do, but it's not necessarily intrinsic to the data science discipline. And you had some thoughts on that?
I'm by a data science. So from my understanding to this question is, it means like the knowledge graph can replacing the data science job, but I think there's still a lot of
no, Dahong, this is more along the lines of the skill set that's involved in this, the skill set that you exercised when you were putting this.
Okay. Oh yeah. I think it's I think it fits to a data science profile, because like the techniques of transforming the relational database to the RDF triples, it's actually using a lot of techniques of Python and this technical skills. So from this perspective, I think it's actually fits into the data scientist profile. But yeah.
So Michael has pitched in with an answer which is comprehensive and clear. Yeah, no, that's all good. And let's see, the conversation continues, but I think we can let that conversation continue because we're at time, and I'm not entirely sure what happens to Zoom when we go over time. I think it just says you're done. But thanks again, Dahong, and thank you everybody who's managed to stay on for this. And we will close this session now, and I wish you a good lunch. And please don't forget that we have the third stream is happening tomorrow afternoon, our time. So sign up for that, and we will see you then. Thank you, everybody.
Thank you.